Hello, welcome to a video on section 3.1, the derivative of a function. So everyone should have started section 3.1, regardless of the section you're in. But I know some of us stopped at example 1, some at example 2, some at example 3. So the purpose of this video is to get to the end of page 2 of the section 3.1 notes. And I'll start by doing example 1. And if you've already seen example 1, you could probably just fast forward and move on to example 2 or example 3. But might be a good review anyway. So for example 1, you're given y equals x cubed. You're asked to find dy over dx, which is the derivative of y with respect to x. And then use this to find the equation of the tangent to curve at x equals 5. So we know the formula for a derivative, which is basically instantaneous rate of change, or find the slope of the curve, which we talked about in section 2.4, to be the following. The limit as h approaches 0 of f of x plus h minus f of x all over h. So in this case, I'm going to plug in x plus h into y and x into y. So now I'm going to have the limit as h approaches 0 of x plus h cubed minus x cubed all over h. Now, we can't plug in 0 for h just yet because we're going to get an expression that's indeterminate. So we're going to have to do some algebra, work out x plus h cubed, subtract x cubed, hopefully h's will cancel, and then we should get our derivative. Now, you could do x plus h times x plus h times x plus h. You could do all that out, which could take a while. Or, if you do remember our binomial expansion, for example, a plus b raised to the third power winds up becoming this. And if it helps, if you think about Pascal's triangle, we can get the coefficients very simply in that manner. So, for x plus h cubed, let x be a and h be b, and this is expression a plus b cubed. We can expand it in this manner: x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over h. Now, I see an opportunity to cancel, which is fantastic. And I also see an opportunity to factor. I could take out an h. And now I think we're rolling here because those h's cancel as well. Because those h's cancel, now I have the opportunity to plug in 0 for h, and I simply just get 3x squared. So what this implies is that the derivative with respect to x of x cubed equals 3x squared. Now remember, we say this is the derivative with respect to x of x cubed. So d over dx is an operation. Kind of like, we had like logs and sine and so forth. So it's something that we apply to x cubed. And that's what I did off to the left here with this whole limit definition of a derivative. And there's going to be a homework problem that will involve x cubed, and you can simply just use that answer we have right here, 3x squared. Okay, moving right along, let's go to example 2. So again, we're asked to find the derivative. Oh, silly me. I forgot that we had to find the tangent, the equation of tangent to the curve at x equals 5. So let me do a different color here. Our slope at x equals 5, of course, is going to be 3 times 5 squared, or 75. And at x equals 5, y is going to be 125. So my equation is y minus 125 equals 75 times x minus 5. That's the equation of the tangent line at x equals 5 for y equals x cubed. Very steep slope, as you'd imagine. Okay, example 2. So now we kind of just go straight to this. And if you're probably wondering, I'm using red because Stanford beat the crap out of USC for the 5th time in the last 7 years. For those who don't know, or 6th time in the last 8 years, sorry. Not a fan of USC football, so sorry if you are, but I had to rub it in a little bit. Anyway, so we're going to take the limit as h approaches 0 of f of x plus h minus f of x over h. I just feel like writing that definition again because I want to make sure you're very comfortable with it. So 1 over x plus h minus 1 over x over h. Now, there's a lot of ways you can combine this. Personally, I like to do this. And I won't fault you for whatever technique you use, but I like to multiply top and bottom by the LCD and just get things to cancel right away. And when I say cancel, I mean the denominators that cancel. So this way, we don't really have a complex fraction anymore. We got x minus parentheses x plus h. So just comes out to be a very clean process. Subtract the x's, we got negative h times x plus h. H's cancel. And don't want to be lazy with the limit notation. You gotta keep writing it because that's what we're doing, taking a limit here. And of course, I just want to gain 1 over x squared. Oops, sorry, negative 1 over x squared. Can't forget about that negative. Do make sure you distribute that negative. Very, very important. So what this means is that the derivative with respect to x of 1 over x is going to be negative 1 over x squared. Okay, then example 3, then the two starbursts down below. Now if you look at this one, f of x equals root x, right? That's what we got. So, and I'm going to use this notation, which is the same thing as f prime of x, or, d over dx of f of x. It's all the same stuff. That's going to be the limit. Again, as h approaches 0 of f of x plus h minus f of x all over h. And again, you can use dy over dx, you can use f prime of x, a lot of different ways you can write the derivative or, whatever. So now our function is root x. So we want to begin this. Now, whenever we see radicals, it's usually a good idea to multiply both top and bottom by the conjugate. Because right now if I plug in 0, I get 0 over 0. It's indeterminate. The hope is that by doing this, I can get the h on the bottom to cancel, and then I can plug in 0 for h for the limit and be all squared away. So by doing the conjugate, I get x plus h. And remember, when I multiply root x plus h minus root x with root x plus h plus root x, that presents a difference of 2 squares. So I get that. Oh, this is lovely. Look at this. This is going to be so nice. Those x's cancel. So I got myself the limit as h approaches 0 of h over h root x plus h plus root x. And my h's will cancel. And now, that's just 1 over all that. I get 1 over 2 root x. So I believe there's going to be a homework problem that will involve that as well. And you could just use that derivative straight up. So in general, if you think about it, if we take the derivative of a linear function, right, the derivative is basically representing the slope of the curve of the tangent line. Well, that's just going to be m, right? And we actually have done x squared before, the slope of a curve at x squared. That's going to be becoming 2x if you work that out. And these are things that we're going to explore in great detail later in chapter 3, how we can wind up getting these a little more efficiently than go through this whole limit process. But it's good to do the limit process since, that's what we take to be the derivative, the slope of the curve, or the slope of the tangent line, or the instantaneous rate of change. Okay, that concludes our video for the first 2 pages of the section 3.1 notes.